could imagine it's exactly like what would happen on Great Sumatran Fault or any more vertical strike slip fault. Then I'll show ideas of dislocations, what is this word, and then I'll show the example of this theory called strike slip parallel displacements from simple screw dislocation, do a few examples, and then we'll do our exercise from Izmit earthquake, so from Turkey, because we have some data. Okay? So this just shows some different parts of the San Andreas fault system, and there was a big earthquake in 1906 called the San Francisco earthquake that was famous for kind of being at the beginning of modern seismology. You know, people started thinking about how earthquakes can work. And so, you know, they talk about elastic rebound and Harry Fielding Reed, the Reed model. This came from there. So, but here's an example from north. So this is up here, right here. And so even in 1906, there was some surveying, you know, with mostly they would use a theodolite. And so you measure the distance and the angle change, and then you can compute the displacement. So the vector scale you can see here is in meters. So these stations, this one moved about 1 meter. But as you see, as you come close to the fault, it gets larger, right? Over like 10 kilometers, okay? And then once we cross the fault, so between 6 and 7 is the fault, and you see the direction changes, right? It's right lateral. And then as we go away from the fault, it goes down again. So this is coseismic signal with the highest displacements at the fault. And so here's an example of some damage. And the famous picture of the surface rupture. So it's just tearing the ground, you know, and here, remember, I was talking about the effect of the vegetation holding the blocks together. And then this was this famous fence that they show that was offset. So the idea of this elastic rebound is, you know, you start at the beginning and you, because of the plate tectonics, you slowly deform, and then in the earthquake, it snaps back, right? Now, one small misconception is that they show always the fence. And so here it's, you know, kind of looks like this. But the misconception is this bending occurs at about 10 kilometers. So it's like if it's a 10-kilometer long fence, you'll see it bend, but not across the field. So it's a small but incorrect way almost every one of these cartoons is drawn when they talk about elastic rebound. So these idea of dislocation is it's called a displacement discontinuity in a continuous body. So it comes from mineralogy. So if you think of crystal, like some salt or something, you know, you have the lattice, these blocks, and you may displace like one unit cell over, but you come down and then at some point you get to the end and there's no displacement. So you kind of make a circuit. You call this the displacement, and then you go around, you follow around, come to the other side, you find it. So this is why this one's called a screw. It's like, you know, if you're screwing something into the wall. And so this kind of looks like a strike slip fault, maybe, you know, just going like this. And then so in this case, the slip is parallel to the tip. The direction's the same, the tip and the slip direction. So the other kind of dislocation is called an edge dislocation. Same idea, but in this case, the motion is perpendicular to the tip. So it's just like an edge. So the mathematics that goes with dislocations comes from the mineralogy people. So crystallographers, they develop this mathematics. So we can try to use it, and it's actually surprising because it works so well. So here's the basic idea. So this is important conceptualization for earthquakes and earthquake cycles. And really, the way I like to think of it is more the thick lithosphere model is the one that is more kind of consistent with how you think the Earth works. And so just look on the left here. But if you have a fault, so you can imagine the San Andreas fault, or you can imagine Great Sumatran fault. You can even do it with a subduction zone, but let's just keep it this way for now. And the two sides are moving horizontally. So we know at depth, usually this depth D, below some depth, it's stably sliding. So what is D? How deep is usually this transition, do you guys think, in the Earth? Usually, well, more 10 to 15. Because it's vertical, it might be 30 kilometers down dip on a gently dipping fault, but it's about, easy way to think is about 10 because of temperature. So like in California, it's about 30 degrees C per kilometer. So by the time you get to 10 kilometers deep, it's 300 C. So it's too hot for frictional processes to dominate. So instead it's slowly just sliding. So you have, for geologists, this would be where we're making mylanites down there. And so we're steadily sliding, but above it's locked. And so you just have frictional behavior. You have to load it up enough, load, and then snaps the earthquake. So what this guy Thatcher, the USGS scientist, it wasn't his idea, but he explained it very simply, was that you could think of the behavior of a fault is kind of two stages, the coseismic and interseismic. And so in a way, the interseismic is what's happening down here, steadily slipping. And so he shows this plot of, so basically y would be distance perpendicular to the fault. So y would on here goes like, is this direction right here, okay, y. And then x would be parallel to the fault. So what he's showing is the displacement parallel to the fault, how it changes as you approach the fault and go away from the fault. And so this steady motion at the far distances is the total displacement, delta U, over time. Let's say over 100 years, 10 meters, okay? But it happens steadily. But at the fault, it's stuck, especially right here. Nothing's happening, so strain's accumulating, and then it has to be released. Boom. And so, it goes like this, and then, and that snap is when this part D slips. And so that part is called the coseismic part, and that's this one here. So same thing, distance from the fault is the Y, but then delta U is the coseismic slip at the fault surface, and it decreases going away from the fault. So the important thing then is that if you just look at this, you say, all right, well, if I add this much right here, and then I come this way, add a little bit there, a little bit there. When you add these two together, it's like block motion, right? So over the long term, it just goes along like this. But it has two stages. It's kind of like, it strains, snap, and then it's going to strain, snap, strain, snap. Okay? So that's the, interseismic, coseismic, interseismic, coseismic. Because the edges of the model is plate tectonics, just pulling things along. But this is kind of like, has this depth variation because of we think the fault has frictional behavior. So this is the cross section. So this would just be a slice, just right through here, just this face. And so what we see in coseismic is just this part moves, and below it's stuck. And then interseismic, this part's always steadily moving below D. Okay? So we'll play with this because these equations are really simple, actually. So you can do it in Excel, and maybe it will be clearer. Because I see your faces, you're like, what? So hopefully, but you have to ask questions because we have to do this together. But let me go through the story a little bit more, and then we'll come back. But just to show the equations, this one says, basically, this is the change in displacement with time. So this is basically the displacement rate is equal to the slip rate divided by pi times a tan of y over d. So this is just the equation for this curve. Okay? And then this one is the strain rate, which is just basically the derivative of this. So the highest strain is at the fault, and it goes down. And the strain is antisemetric for coseismic and interseismic. So when you add these two together, you also get no permanent strain. And that's what I mean by, this strain is balanced with this one. And one important thing, and this is why I'm doing this partially for this class, is that the half width of the strain, or you can think of kind of the wavelength of this gradient and displacement, it's controlled by the depth. So the deeper the fault is, the wider the effect is. Or the shallower the fault, the narrow. And so this is something you always should keep in your mind, how sharp is the displacement field? If it's very sharp, it must be a shallow source. If it's really broad, it must be a deep source. And so this is a way to prove that. So I'll